Okay, so let me thank the organizers for inviting me to give a talk on this subject. So I'll talk about granular geometry of large and matrix models and two-dimensional string theory. So some part of the audience have heard parts of this, but there will be new things in this one. Okay, so let me start. Okay. So matrix field theories have been argued to describe emergent geometries in the large n limit. Examples are ADS-CFT, C equal to 1 matrix model, etc. So in this talk, we'll point out that one may encounter certain inconsistencies in insisting on a continuum emergent geometry from matrix models. We'll show this by focusing on matrix models, which are, by matrix models, I will mean space-time independent matrix models, as well as matrix quantum mechanics, in which the matrices will be a function of time, which includes a C equal to 1 matrix model, which is dual to two-dimensional string theory. So in the case of large n matrix quantum mechanics, we'll find that the inconsistencies are resolved by a lattice geometry, so which I'll also call alternatively granular geometry. I'll explain, of course, what it is. We'll briefly hint at a similar resolution for time-independent matrix models as well. Here, by geometry, we mean a bosonic field theory representation of the matrix theory. For example, note that in two-dimensional string theory, the only dynamical field of the string theory is actually a scalar field. Matrix is non-dynamical. So it's like the bosonic field theory is the only description of this. Okay, so let me go to some specifics. So let's consider matrix models which are space-time independent to see the problem. So consider computing the following thing. So here I'm integrating over n by n matrices, Hermitian matrices with some action given by trace of a certain potential V of M. Here I have taken the potential to be a quartic potential. And what I'm computing is an expectation value of this object. So these are things that I'll call the pth moment. And take, for example, G equal to 0, the simplest case, and P equal to 4. So you can compute this object for P equal to 4, I4, just by plain Feynman diagrams, because this will be, this is just a Gaussian matrix model, and the result is 2 plus 1 over n square. So 2 comes from the two planar diagrams for this contraction, and 1 over n square comes from one non-planar diagram. Okay. Now the question that I'm going to ask is there a continuum description of the above computation? Recall what we are having, what we can have in mind is like a bulk dual of a CFT computation of this kind. So is there a continuum description? So to go towards the continuum description, first note that the questions that we have asked here is UN invariant. So so therefore this computation can be described entirely in terms of eigenvalues. So let's do that. So I make a change of variables from matrix variables to eigenvalues and the angles. And so the angles can be integrated out because they don't appear either in the observable or in the action. So when you do that, there is a Jacobian that you find, which is given by the square of the van der Monde determinant. So with this change of variable, you can write the original integral over the matrices as an eigenvalue integral like this, in which the trace of V of M just becomes like a sum over V of lambda I. Okay, and the square of the van der Monde, that also you can write, put it up in the exponent, it becomes like a double sum of log of lambda I minus lambda J with I not equal to J. And of course the moment, that also becomes a sum over eigenvalues. Okay, so so the standard attempt at a continuum description goes in terms of eigenvalue density. You can define the exact eigenvalue density as a sum of delta functions like this. But in the large n limit, let us say that you want to approximate this by some function. Okay. So here we are attempting a change of variable from a finite number of variables, however large, to some uncountably infinite number of degrees of freedom. This is clearly not justified at finite n, however large, but nevertheless, let's go ahead. So then this integral over the eigenvalues becomes an integral over functional integral over this rho of lambda variable. Okay, and you can easily see that the sum over the v of lambda I becomes an integral rho lambda v lambda, and the double sum here becomes rho lambda prime log of lambda minus lambda prime. Okay, and the observable here, the moment, that becomes rho lambda to the power p. Now, by the way I have normalized this rho of lambda, this action here has an n square in front of it. Okay, therefore you can compute this integral by a saddle point solution at large n. Okay, so this you can do. This is a famous work of Reza and Parisian Zuber, which was also mentioned in Schmidt's talk, and you get this result. Okay, this is the famous Wigner semicircle law, and the I4 basically in the saddle point evolution basically means that you replace this entire, so here you replace rho of lambda by the saddle point value. That's all it means. Okay, so that's what I have done here, and you get 2. Okay, so this matches the leading n equal to infinity result, which is 2 here. Okay, which came from the exact calculation. How about the 1 over n square? Okay, can we obtain the 1 over n square from the rho lambda path integral? Okay, so the answer is no. Why is that so? Because so normally, if you're given a path integral, then of course you have fluctuations over the about the saddle point, and let's call that delta rho of lambda, and you can derive the new expectation value of rho of lambda as this. Okay, and but in this theory, this rho lambda action was strictly quadratic, so therefore you don't have this tadpole-like diagram. As a result, a rho lambda expectation value, even after doing the corrections over this thing, remains rho naught of lambda. As a result, the result from the rho lambda theory remains 2, and you don't get the 1 over n square correction. Okay, so the problem really lies with the change of variable from n variables lambda I to an uncountably infinity of variables rho of lambda. And one way to see this is that a generic rho lambda that violates these trace identities, also called Cayley-Hamilton identities, for any n, however large.
Sorry.
Okay.
Question.
Yeah.
So you said the Jacobian from changing from the lambda i's to the rho, that doesn't help you either?
That does not help me either, because.
How do I see that?
Okay, so there are several ways of saying that. This is a bit of a long story, so I can get back to that one. So there is a Jacobian, which is exponential of n rho log rho, but this is supposed to be cancelled by some counter term that you need to regulate this rho lambda prime log of lambda minus lambda prime thing for Hermitian matrix models. Okay, so there is a claim of that kind, but even if you don't believe this exact cancellation, put this up thing, it's not at the level of 1 over n square. It would appear like 1 over n. Okay, that's another issue. But if I believe the claim that the J of the Jacobian actually cancels against that counter term, then it does not contribute. Yeah. Can you turn on the mic?
the semicircle was saddled without the operator insertion, right?
Yes.
So the operator insertion, if you check for a new saddle, nothing changes.
Oh, that's in the saddle point thing. You know, if you put in some object, it's a standard saddle point stuff. So whatever appears downstairs, it does not, unless it's something very big, it does not change the saddle point. So, all right. So one way to see that, you know, we are doing something wrong in trying, you know, eigenvalue density description is that that any row of lambda should satisfy these trace identities because so here here's how it goes. So at any n, however large, you know, this the system is given in the matrix is given in terms of the in eigenvalues. So there, which can be, you know, obtained from the first n moments, first capital N moments of the matrix. As a result, all the subsequent moments, okay, are writable in terms of the first n moments. Okay, so for example, for n equal to 2, there you can clearly derive some relation that the cubic moment here is written in terms of the trace m and trace m square. Okay, so this is an example of Cayley-Hamilton identity. Now, if you write this in terms of the eigenvalue density variable, that looks something completely weird. That you know, the rho lambda is constrained to satisfy these relations. Okay, so no smooth rho lambda would ever satisfy such trace identities. Remember that there is not just the cube, but even power 4, you know, trace m to the power 4, 5, everything. There's an infinite number of such constraints. And eventually, no smooth lambda would ever satisfy such identities. Actually, the thing is that rho of lambda is actually sum of delta functions. It's a very kinky function. So indeed, from definition, rho lambda is a distribution rather than a function. Hence, a functional integral over rho of lambda is not valid. I mean, it should be at all something like a distributional integral. Okay, so let me go. Yes. Yes, eventually, you know, you can show in this case that this is a solution of the infinite number of you know, trace identities. Okay, this is indeed the solution. Yeah, that is to say, there exists lambda 1 and lambda 2, which will solve this, and that's the only solution. Thanks for the question. Okay, so now let me go to matrix quantum mechanics, where the now allow the matrices to be a function of time. And let me consider again the following computation. It's so now the action has an m dot square time derivative because it's time dependent. It goes from 0 to capital T, and I'm computing again the same thing. It's a moment. Okay, now, so let's go, again, this question is a singlet question. In fact, I'm going to restrict only to the singlet sector of this model. You know, one way of imposing this is by replacing this ordinary time derivative by a gauge covariant derivative with and introducing a gauge field A naught. So either that way or by simple declaration, I'm going to say that I'm going to restrict to the singlet sector of the theory, in which I'm going to, at every time slice t, I'm going to make a change of variable from m to the matrix to the eigenvalues and the angles. And here in this case, what happens is that once you integrate out the angles, there is one factor of van der Monde determinant at time t equal to 0, and another factor of van der Monde determinant at time t equal to capital T. So the initial and the final times get a van der Monde determinant factor. So what it does, because these are completely you know, antisymmetric and eigenvalues, what it does is to make the initial and final wave functions which were sitting you know, at time t equal to 0, and so these guys get you know, multiplied to those wave functions and making the wave functions completely antisymmetric. So finally, as a result, when you do that, when you absorb these van der Monde factors into the wave functions, you get a theory of free fermions where the eigenvalues have now become fermions because of the complete antisymmetry of the wave functions. So what you get is n free fermions on the real line, free because it's a sum over I. There is no ij coupling here. Ij couplings were here, but they have all been absorbed in the wave function. So you get free fermions on the real line with a single particle Hamiltonian given by this. Okay, let me say that for later use, I'm going to introduce the eigenfunctions and the eigenvalues of this single particle Hamiltonian. For example, for the harmonic oscillator, these are the eigenfunctions and these are the eigenvalues. So for the ground state of this series, the field Fermi C, like so, and now you can compute this object, okay, in the So here, what I mean is that I'm computing a ground state expectation value. So so this can be done either by taking this time t going to infinity and 0 going to minus infinity, or you put in explicitly values of the ground state wave functions here. Okay, so now because this becomes a sort of free fermion problem, this moment again for p equal to 4, it can be explicitly computed like this. Okay, lambda to the power 4 and chi n lambda mod square. It just becomes it's a very simple expression to derive, and over the occupied wave functions, and the result is this. Okay, so the leading term is 1 over 2 omega squared, where omega is the frequency of the harmonic oscillator. Now again, the question is there a continuum description which reproduces this? So let us try the eigenvalue description again. Eigenvalue density. Since the eigenvalues have become fermions, the eigenvalue density has the following alternative description: rho lambda is equal to psi dagger lambda.
Sorry, Gautam, I have a question on the previous slide here.
Yeah.
So you also get the 1 over 2 n square from here?
Yes.
Okay.
This is the exact calculation. In the exact calculation, that's what I will do. Just like last time, for the time-independent Betis model. Okay. We'll see, we'll try to see, so what's going to happen is that we're going to get this, and we're not going to get this, okay?
If you're calculating low enough IPs, the low enough moments, you have to still impose all the trace relations to get them, or would you have been fine if, I don't mean here, like the correct way to do it, like?
Yes, for any finite n, however large.
No, what I meant is in the continuum description for the time-independent thing.
Yes.
You said the problem is with the trace relations.
Yes.
But even if I was calculating IP for low enough P, I still have to impose all the trace relations to
yes, indeed.
I can't do it with a few of them.
No.
Okay.
No, yeah. So one thing that you could try is to go from the rho lambda description to the moments description. Okay, so I can tell you that. Yes, indeed, you have to put all the trace relations. Yeah. Even though the observable is not is one of the independent variables, but the path integral has all these trace relations. So that's what the. Okay, all right. So good. So this eigenvalue density now can be alternatively written in terms of the second quantized fermion field, which is given in terms of this. The chi and lambda are our wave functions, Hamiltonian eigenfunctions, and these are the oscillators, fermionic oscillators, psi n and psi n dagger. And so Das Jivicki wrote the following density representation for the matrix path integral, which is called the collective variable. So rho of lambda here is written in terms of the derivative of this variable zeta, and the action looks like this. And again, there is an n square sitting outside of this. Therefore, you can compute the saddle point solution. And so this is this famous saddle point solution, which is related to the WKB momentum of the Fermi level, and it's given by this. And so the this is like the Bohr-Sommerfeld quantization condition for the Fermi level wave function for the Fermi level, and for the harmonic oscillator potential, you can compute this and plug in this rho naught of lambda in the moment relation, and you get 1 over 2 omega square, which is the correct expression for what we got from the exact calculation. Now the question is, can you get the subleading correction? This one? Yeah. No, this is not exact, because here from the matrix variables I have made a change of variable from like mij of t, which is the n square functions of t, to rho of lambda comma t. Okay, so that's one function of two real variables. That's too many. Okay, so it's not an exact translation. Okay.
Sorry, but
yeah.
You can still think about it. Like, think about such a correction. You can still think about whatever n squared correction to be like infinite genus type of correction, right? Coming from the
genus 1, you mean? One loop.
Oh,
1 over n square correction
yes,
is like
still if you write it in this continuous variable, I guess you interpret it as it's coming from the.
That's right. So I'll compute the one loop correction now, and we'll see what happens.
Very nice, thank you.
Yeah, indeed, in this theory, this is not a quadratic theory. This is a cubic theory. So therefore, there will be a tadpole now. So let's compute that. So indeed, let's compute the expectation value of delta rho of lambda. That is like this diagram. Okay. And it correctly comes with 1 over n square. So one factor of 1 upon n comes with the definition of delta rho of n, because n square was my saddle point parameter. And the other one is that the cubic term around the saddle point. So in this, if you expand this around the saddle point value, then you will get 1 over n in the cubic term. Okay, so what I'm doing here is to use this expression so that the cubic term has an overall 1 upon n. So this vertex has 1 upon n, and my observable has 1 upon n. As a result, this is 1 upon n square. So the order is correct, but this is actually a divergent diagram. Okay. So the loop integral involves a coincident propagator and is divergent. This gives an infinite contribution at this one, whereas the exact result is this. Okay, you may say, how about adding a counter term to this theory and getting? So I'll get back to that issue when I go to the C equal to 1 matrix model. What happens with the counter term and so on. But at the moment, this is what we get. So once again, we do not get the correct results in the change of variables. So this is in answer to somebody Chetan's question. So this is not an exact change of variable. So we'll resolve this problem by an exact transformation of variable from the eigenvalues to a lattice boson field, where the lattice contains precisely n points. So let me. So that was about the moment calculation. So in this matrix quantum mechanics, there is another important calculation that you can attempt to calculate, which is the entanglement entropy of an interval A going from lambda 1 to lambda 2, in the eigenvalue direction. So in the ground, let's say I take the system in the ground state, and what is the entanglement entropy of this interval? Okay, so we can answer this question. So fortunately, Shumit described this problem in some detail, so I'll skip the details here. So we can answer the question in various ways. One is target space entanglement entropy, something that Shumit described in detail, and this is also equivalent to the other way of doing it, which is the usual QFT, base space entanglement entropy in the fermion theory. This is given by the following formula. So it's it involves the occupied state wave functions of the, and this is the formula that this is what is called the quadratic cumulant. That's the leading large N formula for this. And so I have written the formula back again here. This is clearly, obviously finite, right? Because it goes over a finite number of levels, and the areas, I mean, the integrals are also over finite domains, and the wave functions are all regular functions. So this is obviously finite. In this 2D string theory context, this was computed and shown to be finite by Schmidt, which was later refined by Hartnoll and Mazenk. And we'll come back to the 2D theory later on, but you can compute this, for example, for free fermions, which is the box potential for fermions, and it's easy to compute because these are all either sine functions or exponential functions, and you just get this. So it's 1/3 log lambda 2 minus lambda 1 divided by epsilon, where epsilon is given by L upon N. Okay, that's the inverse of the Fermi momentum. Okay. For fermions in an external potential, this was for free fermions, no external potential. So for fermions in an external potential, the result becomes this way, where lambda naught is some point, any point in the interval lambda 1 to lambda 2, and it's given by the WKB momentum of the Fermi. This should be EF.
Sorry, Gautam, could you remind what lambda 2, lambda 1, and L is?
Yes. So lambda 1, lambda 2 are the endpoints of the interval for which I am computing the entanglement entropy.
And what is capital L?
Capital
Equation 2.
This one is defined. Oh yeah, sorry. This is the free fermions for in a box of length L, length capital L, which is taken here to be large enough compared to the interval size lambda 1 to lambda 2. Okay, so right. So this is the formula in the presence of a potential, and this is in case where the potential is not varying appreciably within the interval lambda 1 to lambda 2, and this lambda naught can be taken to be any point in that interval. More sophisticated formulas also exist. Can we get this formula from the density variable, which is the collective variable theory? For a bosonic field theory, the entanglement entropy of a region, this formula has appeared in various talks, including Shumit's talk and Rajdeep's talk, and in Rajdeep's talk, I think. So you take the phi correlator and the pi correlator of the bosonic theory, construct this matrix C, where these are all x and y are points in the interval A, and then you construct this quantity that gives you the bosonic field theory entanglement entropy of this interval lambda 1 to lambda 2, and so this. So if you restrict the collective field theory to quadratic fluctuation, that just gives you a massless relativistic scalar field theory, for which this quantity just becomes 1/3 log lambda 2 minus lambda 1 over epsilon, where epsilon is the short distance ultraviolet cutoff. So this object is divergent. Okay, this result is divergent. It requires a regulator, but it agrees with the fermionic result or the matrix quantum mechanics result if we choose epsilon to be L by N. But of course, this theory does not have such a regulator, so therefore it's a divergent result, and it does not agree with the fermionic result or the matrix quantum mechanics result, which is the same thing. Okay, we'll find that equation 2 as well as equation 2a can indeed be reproduced. So these are the fermionic results, can indeed be reproduced in terms of a lattice boson with the above lattice spacing. That's to come. So here I was talking about only the quadratic fluctuation. What about the full collective field theory? So Shumit has already described this, that in their work in 2022, they showed that the fermionic 10 minutes. All right. So in case in case of particles in a box, there is a sort of the fermionic entanglement entropy has the bosonic interpretation, which gives the correct finite result. Although it is not clear whether the bosonic entanglement entropy is obtained in that fashion. See Shumit's talk for more details. So summary so far, in case I don't finish in time. So here is what we saw. A continuum description of matrix models in terms of eigenvalue density rho lambda is inconsistent with trace identities, which prevents an exact change of variables from matrix degrees of freedom to rho lambda. Okay, basically the trace identities sort of prevent you from this change of variable. Rho lambda description fails to reproduce 1 over n expansion of moments like trace of m to the power p in both the time dependent and time independent case. So what you reproduce is the leading n equal to infinity term, but 1 over n does not work. In the c equal to 1 model, this is something that we'll see. It also fails to reproduce the perturbative expansion of the 2D string S matrix. Okay, this has not come yet, but I'll mention that later. In case of matrix quantum mechanics, the eigenvalue description does not reproduce the leading large n expression for the entanglement entropy, which is this way, which is non-perturbative in n. For the box potential, it's like log of x2 minus x1 times n. So it's what's coming in the next 8 minutes is that we'll discuss an exact bosonization of matrix quantum mechanics, equivalently an exact bosonization of 1D non-relativistic Fermi gas, which is the same thing, valid for any n which incorporates the trace identities. The bosonic field can be regarded as living on a lattice of n points, which is what we call a granular geometry, which are in one-to-one correspondence with the n eigenvalues. There are n eigenvalues, and I'm going to use a lattice of n points. So as a result, it is one-to-one. This new bosonization solves the above mentioned problems, including that of the perturbative 2D string S matrix. Okay, so how does the exact bosonization
Sorry,
go?
Gautam, can I ask one question before
Yes.
you go on? So,
Yes.
so this 1/3 log formula
Yeah.
from the 2D target space point of view looks like a tachyon field that is just moving.
Right.
But there's also some dilaton, right, in the background.
Yeah.
And typically in 2D dilaton systems, there is a contribution which is dilaton over 4G to the entropy, like in JT gravity or CGHS model, I think. So is the contribution there in this case or not? Just dilaton over 4G Newton?
That is a very good question. So I think it is, this one is not that. Okay, this one is...
This is like the one loop fluctuation of the matter, the tachyon matter on top of that.
Yeah, probably. But maybe Shumit or Ashok can have better answers to this. Yeah, that's a very good question. I don't have a good answer. Okay, so yeah, let me go very quickly. So how do we do this? This is based on some earlier work with Avinash and Nemani. So let me first review that part, what we did at the time, and then the new thing that we did now in terms of lattice bosons. So if you have just one particle, there's no distinction between fermions and bosons, and then you can invent ladder operators, A and A dagger, to go up and down, along the fermion spectrum, and such that A dagger equal to 1. So these will be like my bosonic oscillators, annihilation and creation operators. And in terms of the fermion bilinears, they look weird, but this expression just means that this is what they're doing. Okay, so this is for n equal to 1. For n equal to 2, now I have two fermions. Okay, the states are like F1, F2, ket, and I'm plotting here in this two-dimensional lattice of kets. F1 on this direction and F2 in this direction. Now it's not clear how to describe my ladder operators. So it turns out, okay, which you should accept my word for it here, that sigma 1 dagger, okay, the raising operator for the second, so there are two raising operators and two lowering operators, which become in the bosonic theory the two creation operators and two annihilation operators. So the raising operators in this case are a little funny. Sigma 1 dagger goes up and sigma 2 dagger goes along the diagonal. Okay, so if you do that, then define your sigma 1 dagger, sigma 2 dagger like that, then they have some, and then further normalize these operators in a certain way, then the A and A dagger operators, they satisfy this Heisenberg algebra, and you can find out from here an exact mapping between the, okay, so the bosonic, so the fermionic states are given by F1, F2, bosonic states are given by R1, R2, and there is a relation between these which you can find. So it's an exact isomorphism between the fermionic states. And okay, so this is how you do this. I don't have time to explain for n particles. So now the sigma k dagger is an operator which raises all the top for n top k number of occupied fermion levels by 1 up, starting from top down, and sigma k is the conjugate of that. They have a funny algebra, sigma k and sigma k dagger, like this. It's not Heisenberg algebra, but once you do this, then you get a Heisenberg algebra. So you get an exact Heisenberg algebra in terms of this. I'm going to flash in a slide how these A and A daggers are related to fermion bilinears. But importantly, there are only in this case, there are only n number of oscillators here. Just like in the previous slide, I had two oscillators, A1, A2, and A1 dagger, A2 dagger. Here also it's like that. Finite number of bosonic oscillators. So the bosonic field theory therefore has an inbuilt cutoff because it has a finite number of modes. Okay, so that's the that's where the finite UV cutoff comes from, and therefore the results that you get finite are because of this fact. Okay, and now there is an exact correspondence between the fermionic states given by this integers f1 up to fn. These are the filling of the arbitrary state, and this r hat, the r vector is the occupation numbers, and the relation between the filling numbers and the occupation numbers is this. Okay, and one important thing to note is that with this correspondence, the fermion ground states becomes the bosonic ground state, and that's just the zero particle state of it's annihilated by all the. Okay, so this here there's some nice group theory of how this. This is a rather mysterious, thing that I said, but they actually have some beautiful, group theory reason for inventing the operators in this fashion. But let me not go into that. It comes from some history of, the story of giant gravitons, but I don't have time to go to this. Okay, so let me tell you how. So this was about. So I said how the one-to-one mapping between states in the Hilbert space goes. So now I can also map the fermion Hamiltonian to the bosonic Hamiltonian. So on a particular the state described by the fillings like this, the the energy is given by the energy of the state Fn, right? Now Fn's, which are the filling numbers, they are related to the occupation numbers of the bosons in this way. So therefore, this is a certain function. Epsilon of Fn is the energy of the Fn mode, but Fn becomes like this. Okay, so therefore it's a certain function of this combination. Okay, so what bosonic Hamiltonian acting on the Fn's, okay, produces this result? It's very simple. So we just replace each of these r RKs, the occupation numbers, by the A dagger I, corresponding A dagger I. Oh, all right. So you can describe a Hamiltonian, and so this is the promised, one-to-one map between the A daggers and the fermion bilinears. So this, for the free particle case, you have, can I take okay, for the free particle case, fermions in a box, the total Hamiltonian becomes the constant plus H1 plus H2, where H1 is the, is the dominant part at large n, which has a linear dispersion relation. So just remember this, we will use this. Okay, so applications of this, calculation of moments. So now here's an explicit computation of the moments that you can do by using this, formulation. And what you can show here is that you get this, 1 over 2n square, the finite n square corrections. And in the calculation itself, you'll see that the result was finite in case of the fermions because finite number of fermions. Here, there's a finite number of bosonic modes that makes it finite. Okay, so this is an explicit thing. And the bosonic theory reproduces the fermionic moment exactly. That's not a surprise. And in the collective field theory, a similar sum like here had an infinite number of modes. As a result, it gave you something divergent. Okay, so for entanglement entropy question, the question is slightly more involved. We have to now, if we want to ask the question in the bosonic theory, we need to invent a real space for this bosonic theory because earlier we only had oscillators, So now that's what we do. It turns out that in order to place the oscillators, and invent a real space, you need a lattice with a finite number n of points. And then, let me just, so this is something that you can show explicitly that this, the phi j and pi j guys, they are also in one-to-one correspondence with the fermion bilinears. So it's an exact translation even at this stage. And, what we showed is that, this is one, so the low temperature partition function shows that the fermion Hamiltonian here, okay, and the relativistic boson Hamiltonian at low temperature, this H1 tilde is an approximation of the total Hamiltonian, which is H1 plus H2. But this approximation is very good, and it gives you actually, the agreement with the. So this is beta. So that side is this side is low temperature. So but otherwise, of course, you do have the full Hamiltonian at your disposal. But the lattice boson becomes very simple if you are at low energies or at low temperatures. Okay, so the entanglement entropy also comes out correctly. So one way to see this is that in this problem, when I can approximate the Hamiltonian by this Hamiltonian, which is equivalent to this lattice boson, then of course it is known from earlier that it is, the entanglement entropy is given by 1/3 log L. L is like, x2 minus x1, the length of the interval, divided by some epsilon, where this should be just epsilon. I don't see why there's an epsilon prime, where epsilon is the lattice cutoff. Now we do have a lattice cutoff, and that lattice cutoff turns out to be the same as what happens in the fermion theory. Okay, so that's the main point that I wanted to say here. So the entanglement entropy also comes correctly. I don't have time to say what happens in the presence of a potential. In case of a potential, the lattice geometry has to be non-uniform. Okay, and then it comes out correctly again. And this can be, okay, so let me just say that for the C equal to 1 matrix model, okay, just 2 more minutes. For the C equal to 1 matrix model, this is the matrix quantum mechanics again with a potential which you can take to be like this. And the important physics comes when the filled Fermi level, the filled Fermi C reaches near the top of the potential. And here, the entanglement entropy is given by this by the previous formula that I wrote down. So as we saw above, this result can be obtained from the fermionic formulation as well as the exact lattice boson that we described above. And sorry, excuse me. Yeah. Now let's do the. So we get this formula for this potential, and now we can take the double scaled C equal to 1 matrix model. So when we turn on the double scaling, then what happens is that the three ingredients that are there in the entanglement entropy formula, one was the Fermi momentum, that picks up a factor of 1 over square root of n. Lambda 2 minus lambda 1 picks up a factor of 1 over square root of n. And there was a 1 over h bar, which is like this beta n here, that picks up a factor of n. So as a result, this is what happens. The entanglement entropy eventually gives you something finite, all the n's disappear, and you get this formula in which it, you get this formula as a surprise. This was first pointed out by Schmidt in his paper. This as a surprise, as the role of the short distance cutoff seems to be played by epsilon equal to LSGS rather than just the string scale, string length LS, which is what one a priori expects in a string theory calculation. And okay, so this is the S matrix has some similar phenomenon that the in recent works by Sheehan et al. The one tachyon going to one tachyon S matrix was computed in the Fermion theory by us in 1991 and more Ram Gulam. And the result is that there is a tree level correction and there's a one loop correction. This one loop correction you can try to compute in the from the collective field theory, which we did in 1991. What we found was that the one loop term, okay, has a divergent diagram. And you can actually remove the divergence by a counter term, but the remaining finite expression differs from the S1 here. Okay, so on the other hand, in our new bosonic formulation, the one loop term in the S matrix is exactly reproduced, which is okay. So let me not go into this boson. Okay, so this is just one slide thing to say that a lattice boson version seems to also work for unitary matrix model. This is some work in progress, and this is the conclusion. Sorry for going over.
One or two quick questions.
Is it possible to go backwards? Like, how do you correct the wrong results by like coarse graining what you did? Is it possible to do that?
By doing something to the collective theory so that it becomes correct?
So that it becomes like incorrect in a sense. You have the correct description and you do something, do you get the incorrect result?
In other words, I think what you are saying is that can I include correction terms to the collective field theory Lagrangian so that it gives the correct result? Is that what you mean?
No, I was just asking. You have lattice boson description.
Oh yes,
and,
yes.
I see. Coarse grain it somehow.
Yeah, so that's a very important question. I mean, so for example, this coarse grained version that I have, how does it, sort of go over to the collective field theory description, perhaps with corrections and all. Yeah, this is something that we are doing at the moment. And the other important thing is about the C equal to 1 matrix. Yeah, I forgot to emphasize this. In the C equal to 1 matrix model, I have taken the limit n going to infinity, okay, and something else going to 0, so that it's a double scaling limit. So my finiteness arguments in the previous parts of the talk were always by saying that, well, n is finite, however large, therefore it's finite. Okay, but in the double scaled limit also it becomes sort of finite. So actually I need this lattice boson in that limit, okay, in which it actually becomes like an infinite number of points, but with a certain density. So this is something we are almost there, okay, that how to do this computation, this bosonization in the double scaled theory itself, and then compute the entanglement entropy. At the moment, what we did was to compute it in the finite theory, to take the expression of the entanglement entropy and take the double scaling limit in that, and show that it's finite. But it seems that it's possible to go further and first do the mapping for the double scale theory and so on. But it's also related to the question that you asked. Yes, I think so, because indeed, as Shumit mentioned in his talk also, this, this 1 over GSLS appearing inside the log, okay, this is something non-perturbative. So presumably, if we can, complete this exercise of doing our lattice bosonization in the limit in which it becomes a continuum, then it would be something like a non-perturbative thing indeed.
Okay, if no further questions, let's thank Gautam again.